Section 2.7, Derivatives and Rates of Change. We now go back to the ideas of the tangent lines that we saw earlier in Chapter 2. What we saw was that by using the secant line through points P and Q on a graph of a function f of x, the slope of the line through P and Q was m subscript pq equal to f of x minus f of a divided by x minus a. We can do this on any simple graph. So for example, if we had a parabola like this, and we call that f of x, then we can pick some point a f of a, and then any other point just defined by the function x comma f of x, and we can find the line that connects those 2 points, and then therefore find the slope of that line. That's what this simple little formula here represents. The points had coordinates back earlier in Chapter 2, P for A f of a, and Q for x f of x. That's where the subscript PQ comes from. If we found this slope approached a value m, then we said that m was the slope of the line tangent to f of x through P. And the idea with if we found that this slope approached a certain value was this idea that if we made our point x f of x just get closer to a f of a, then we are starting to approach a tangent line at the point a f of a. So as the secant line slope is approaching the tangent line slope, that was happening as the point f of x f of x, which was approaching a f of a. So then this leads us to a definition. The tangent line to the curve y equal f of x at the point P, a f of a, is the line through the point P with slope m, now using our limit definition, where m is equal to the limit as x approaches a of f of x minus f of a divided by x minus a. Essentially, we have the slope formula in that fraction, y2 minus y1 divided by x2 minus x1. But we're saying as the x values are getting closer to each other, then that slope is approaching a certain value. We can rewrite this another way if we let h equal x minus a. And then that means that x is equal to a plus h. So I can replace in the numerator, instead of f of x, I would have f of a plus h, and then minus f of a. In the denominator, instead of x minus a, I have h. And then if x is approaching a, that means that h is approaching 0. So we can rewrite this slope of the tangent line simply as the limit as h approaches 0 of the difference quotient f of a plus h minus f of a divided by h. Let's look at a simple example. This is example 2 on page 142 of our book. Find an equation of the tangent line to the hyperbola y equal 3 divided by x at the point 3 comma 1. So here we can say that if our point is 3 comma 1, then we know that a is 3, to use the language of our definition above. We also know that f of a is equal to 1, which is also just seen by taking 3 for x and plugging it into this equation, and you would get 1 for y as the output. So then what we really just need to find is the slope. The slope of this tangent line is m equal to, and let's use the first definition, the limit as x approaches, in this case, 3, of our function f of x, which in this case is just 3 divided by x, minus f of a, which we've already written down is 1, divided by x minus 3. So if we were to use this version of the definition, because either one is acceptable, we would just start in this case with finding our slope m and trying to evaluate this limit. And of course we have the idea that it is possible the limit will not exist. If the limit doesn't exist, that actually tells us something about the slope of the tangent line, and we'll get to that in a little bit. But for now, let's just see if we can evaluate this limit. If I was to use direct substitution, like we've seen in other examples, that would mean that I would plug in 3 for x because I essentially have a rational function here. But that would give me 3 over 3 minus 1 divided by 3 minus 3, which turns into 1 minus 1 or 0 divided by 3 minus 3 or 0, which tells me that I have a hole essentially in this graph, which means that there is some way to simplify this by canceling out some common factor. So I'm going to take that difference quotient, 3 divided by x minus 1, all divided by x minus 3, and see if we can simplify this in some way. First thing I can do is, in the numerator, get a common denominator. So in this case, that would be writing 3 minus x over x, and then dividing that all by x minus 3. That gives me 3 minus x divided by x, all divided by x minus 3. This is a compound fraction, so now I should write this as the numerator, 3 minus x divided by x, times the reciprocal of the denominator, which would be 1 over x minus 3. And I can see that if I do something with that numerator 3 minus x, I will be able to cancel something out. What I have to do is factor out a negative 1. Negative 1 times x minus 3. If I was to redistribute that negative 1, I would get back to 3 minus x. And I can see that if I do that, then I'm able to cancel out the x minus 3 factors by division, and this leaves me with just negative 1 divided by x. So when I go back to my limit, now I can just rewrite this entire messy fraction as simply negative 1 divided by x. So the slope, m, is equal to the limit as x approaches 3 of what I had before, 3 minus x minus 1 divided by x minus 3. I can now rewrite that as the limit as x approaches 3 of negative 1 divided by x. I can again use direct substitution, and this just becomes negative 1/3. And notice that's my slope. That's the slope of the tangent line. So the equation of the tangent line can be easily written now if I just use the point slope form of the line, which means use a point that's on the line, which we already know, 3, 1, and then use the slope that we just found. So this would be the general form, y minus y1 equal m times x minus x1, but then plug in my point and my slope. So my point will be 3, 1, so the y value is 1, while the x value is 3, and then the slope is negative 1/3. And we could then take this point slope form and write the slope-intercept form of the line, if we would prefer that, y equal mx plus b, by just solving for y. So I can distribute the negative 1/3, and then I can get y all by itself. And there's our slope-intercept form. Either one of these are acceptable because they are both an equation for the exact same line. So really all we've done here is just use the limit to find the slope of the tangent line. Once we have that, then we're just using algebra to write the equation of that tangent line. I will point out that using the first definition, the limit as x approaches a of f of x minus f of a divided by x minus a, is much more difficult to use than the other definition. And so when you see me do another example of this in this section, I'm going to use the second definition just to show you why that's a little bit easier to use. So now, continuing on, back at the beginning of chapter 2, after we talked about this idea of the tangent line, then we also talked about the velocity problem. So let's apply what we just learned, this new definition of how to find the slope of a tangent line, to the velocity problem. To determine instantaneous velocity, this is going to be our goal. We want to determine that. Back in the beginning of chapter 2, we were using a table of values to approximate or take a guess as to what the instantaneous velocity was. So to determine instantaneous velocity, we looked at how time intervals got shorter and shorter, which means that the time interval approached zero. Thus, we investigated average velocity, which we found with average velocity is equal to displacement, the change in position, divided by the change in time, and we can write that as f of a plus h minus f of a divided by h. And then we let the length of the time interval approach zero. So essentially no time was going by to give us this idea of instantaneous velocity. So using our language that we just introduced, we get that the instantaneous velocity at time t equal a is v of a, meaning the velocity at time a, equal to limit as h approaches 0 of f of a plus h minus f of a divided by h. So let's revisit a similar problem to what we saw at the beginning of chapter 2. Number 14 on page 149. If a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by capital H equal to 10t minus 1.86 t squared. So first, part A, find the velocity of the rock after 1 second. We see the word velocity here, so this is really saying what is v of 1. And we're just going to use this new definition that we just learned. Part A is saying v of 1 is equal to the limit as h approaches 0 of our function. Notice that it's f. I'm going to use capital H for our purposes because that's the name of our function. Of, in this case, a is 1 plus lowercase h minus capital H of 1. Again, a is 1 and f is our function, which is in this case capital H. And then divide this all by lowercase h because we are taking the limit as lowercase h approaches 0. So the first thing that I can do is evaluate my functions. What is capital H of these values? This just means plug in what's in the parentheses into my function. So capital H of 1 plus h just means everywhere that I see a t in my function, I'm going to now replace it with 1 plus h. So that would be 10 times 1 plus h minus 1.86 times 1 plus h quantity squared. So that's h of 1 plus h. And then capital H of 1 just means plug in 1 everywhere that I see a t. So in this case, I'll have minus. When I plug a 1 in for t, I'll get 10 times 1, which is 10. And then 1.86 times 1 squared, which is 1.86, and I'll just be subtracting that. So what I have here in green, that's the capital H of 1 plus h, this part. What I have in red is just capital H of 1. And then I have to have all of this divided by lowercase h. So now we want to simplify. We've seen enough of these difference quotients that we've then taken the limit of, and really what we see is if we simplify things, well, they just get simpler. So I still have my limit as h approaches 0. And then I want to just multiply everything out. So 10 times 1 plus h, that's 10 plus 10h. minus 1.86 times 1 plus h squared, which is 1 plus 2h plus h squared, where all I did was just take 1 plus h and square it, which means 1 plus h times 1 plus h. Using the FOIL method, that's 1 plus h plus h plus h squared. That's how I get 1 plus 2h plus h squared. And then minus what's in red, which means minus 10, but then plus 1.86. And then divide all of this by h. And you can see that we have a couple things we can cancel out. Like this 10 right there will cancel out with the negative 10. If I do one last bit of multiplication, I'll have 10h minus, now I have to distribute 1.86 to all of those terms. So minus 1.86 times 1, and then minus, if I multiply 1.86 times 2, that gives me 3.72, so minus 3.72h minus 1.86h squared. And I still have this plus 1.86 at the end there. And you can see I can cancel out a little bit more, the negative 1.86 and the positive 1.86. I also have these h terms that I can combine. So 10h minus 3.72h. And so this leaves me with the limit as h approaches 0 of 6.28h minus 1.86 h squared, all divided by h. And we resist the temptation to just start crossing things out because we want to do this correctly. The numerator has a common factor of h. So I'm just going to factor that common factor out. H times 6.28 minus 1.86 h, all divided by h. And so now we can see that we get to cross out the common factor of h in the numerator and denominator. And now we get something very simple. The limit as h approaches 0 of 6.28 minus 1.86 h. Which means I can plug in 0 because that's just a polynomial, and I can use direct substitution, and I get 6.28 minus 1.86 times 0, which is 6.28. And now what we just found, remember, is the instantaneous velocity of the rock at 1 second, meaning after 1 second has passed, what's the instantaneous speed? And so now we just figured out it's 6.28, but the units of measurement, we have to use meters per second because that's our displacement, distance, divided by time. So meters per second is our units for our answer. All right, so then part B is very similar to part A. In this case, in part B, find the velocity of the rock when t is equal to a. This just means we're finding what's defined up here, v of a. And it's all pretty much the exact same work. So let's just run through that. Part B, v of a is the limit as h approaches 0 of, in this case, again, our function is h of a plus lowercase h minus h of a. You can see that all we've done is just, instead of using 1, we're just using a. And I can plug in those expressions just like I did when I had 1 plus h and 1. So this will be 10 times a plus h minus 1.86 times a plus h quantity squared, and then minus, instead of 10 times 1, it's just 10a minus 1.86a squared. Oh, but I forgot my limit at the very beginning. So let's just erase that, and let's move this stuff over just a little bit to make room. And then I have, of course, I still need all of this divided by h. And I can just keep expanding. So in the numerator, I'll have 10a plus 10h, and then minus 1.86 times, this will be a squared plus 2ah plus h squared. Again, just squaring a binomial, that's all that is. Minus 10a, and then plus 1.86 a squared, all divided by h. And just like we had seen the 10s cancel in the previous part, because that was 10 times 1, I'll have 10a cancel out. You might also remember that we had canceled out later on the 1.86, which came from 1.86 times 1. Well, I'm going to have the same thing here, because notice this is a positive 1.86 a squared, but then after I distribute the negative 1.86, I'll get a negative 1.86 a squared. So just by going off of what I already know will happen from my previous example, now I can rewrite the numerator as 10h minus, we've already said that 1.86 times 2 is 3.72, and this will be a times h, minus 1.86 h squared, all divided by h. And now here again, I'll just factor out an h from the numerator, just like we did before, and I'll have 10 minus 3.72a minus 1.86 h, all divided by h. And I know that then I can cancel out the h factors. And then when I plug in h equal to 0 with my direct substitution step, I'm just going to be left with 10 minus 3.72a. And what this now tells me is the velocity at any time a after this rock has been thrown in the air. It's essentially a function, which is important to us because the next section goes into more detail about the derivative as a function. So then the last two parts of this question, when will the rock hit the surface, and with what velocity will the rock hit the surface? So these next two parts are really a little bit more of an analysis of what we now have in front of us. So when will the rock hit the surface? This means that the height is equal to 0, which we don't even need anything about the velocity. We just need the original function that we got. So part C, the rock hits the surface when the height is equal to 0, which, since we have a function for the height, 10t minus 1.86t squared, we can now just solve that for t. And we can solve that by factoring. Factor out a t. We're not going to do any division. We're going to set our factors equal to 0, which just means that t is equal to 0. That's really when it was thrown from the surface. And then 10 minus 1.86 t equals 0, which means t is equal to 10 divided by 1.86. And if we simplify that, just get some sort of estimate, 10 divided by 1.86, approximately 5.4 seconds. s for seconds. So at 5.4 seconds, the rock will have returned to the surface. And now we can use this answer to answer part D. With what velocity will the rock hit the surface? Remember that this idea of t equal a means any time for t. So I can use my velocity expression that we got in part B. So part D, with what velocity does it hit the surface? That's just velocity at the time, our approximation 5.4 seconds, which just means 10 minus 3.72 times 5.4, which equals 10 minus 20.088. Which gives us a negative answer. Negative 10.088. Again, this is a velocity question, meters per second. Why is the velocity negative? Because the rock is heading down to the surface. So the orientation of the direction, if it's going up, velocity is positive. If it's going down, the velocity is negative. So now we're already starting to see an application of this limit stuff that we've been looking at in Chapter 2, and then we're applying it to this idea of instantaneous velocity. So then from these ideas, what we saw in the beginning of Chapter 2, introducing this concept of the tangent line and then trying to approximate the slope of the tangent line, and then instantaneous velocity, and now with our new language of using the limit, it's from all of this that we get the definition of the derivative. And that definition is the derivative of a function f at a number a, denoted by f prime of a, that's the notation for this, is f prime of a equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h, if this limit exists. And just like we saw there were two definitions for finding that slope of a tangent line, we could also write the derivative of a function as f prime of a equal to the limit as x approaches a of f of x minus f of a divided by x minus a. Again, you're more often than not going to see me use this definition here because it becomes a little bit simpler to simplify those difference quotients. But the second definition, this one gives us a clue as to why it relates to the slope of a tangent line, because we see the difference of output values divided by the difference of input values. So let's look at another example. Number 31 on page 149, find f prime of a, meaning the derivative at a of the function f of x equal to 3x squared minus 4x plus 1. So again, just using our definition, f prime of a is equal to, and all I'm going to do is just start with my definition. Limit as h approaches 0 of f of a plus h minus f of a divided by h. And now we'll just plug in. The limit as h approaches 0. F of a plus h means everywhere that I saw an x, I'm now going to replace with a plus h. So that will be 3 times, instead of x squared, it's a plus h, quantity squared. Minus 4, instead of x, it's a plus h. And then plus 1. But then for f of a, the second part of this difference in the numerator, I'm just plugging in a anywhere that I saw an x. So 3 instead of x squared, now it's a squared. Minus 4 instead of x, it's a. and then plus 1. Just function evaluation. That's all that is. And now, just like we saw in the previous examples, we want to simplify this entire numerator. So multiply everything out. 3 times a plus h quantity squared. We saw that in the last example. That's a squared plus 2ah plus h squared. Minus 4 times a plus h, that's minus 4a minus 4h plus 1. And then minus everything in the second set of brackets. So minus 3a squared. Minus negative 4a, which really just means plus 4a. And then minus 1. All of this divided by h. Like we saw in the previous examples, we've got some things that will go away, like the negative 4a and the positive 4a. And the positive 1 and the negative 1. Let me distribute that 3. And we get 3a squared plus 6ah plus 3h squared minus 3a squared. And we see that we get a little bit more that will cancel out, the 3a squared. So we've simplified the numerator. If you remember what we did in the previous example, you know what comes next. I'm going to factor out an h from the numerator. And so I'll just do that. That gives me an h times what's left, 6a plus 3h. And then all of this is divided by h. Oh, I'm noticing I forgot a term, didn't I? That minus 4h right there. So let's see, let's put that term right here, minus 4h. Let's put that term right there. And let's put that term back here so we don't forget about it. I forgot the negative 4h a couple lines up, so I've circled it in blue, and anywhere that I wrote it in blue is where I was adding it back in. So now that I've factored out my h from my terms in the numerator, I can cancel those out. And I have the limit as h approaches 0 of 6a plus 3h minus 4. I can now use direct substitution by plugging in h equal to 0. The limit expression, remember, will go away at this point because I'm actually evaluating the limit. And now all I have is just 6a minus 4. So now with a couple of the examples that we've seen so far, we've actually taken derivatives of a couple of quadratic functions and a rational function earlier on. So you're already starting to see this idea of taking the derivative of a function, which is what we will talk about in the next section. So this new definition allows us to rewrite some of the detail with the tangent line. So meaning I've got some new notation, this f prime of a. The tangent line 2y equal f of x at the point a comma f of a is the line through a f of a whose slope is equal to f prime of a. If you also remember what we wrote with the point slope form of the line, this means you can write the equation of the tangent line like this. Y minus f of a, that's the y value, equal to the slope f prime of a times x minus the input, a. So let's find an equation of the tangent line to the parabola y equal x squared minus 8x plus 9 at the point 3 comma negative 6. So again, you know what to do from our previous work. We need to find the slope. The slope is just f prime of, in this case, 3, because that's our value for a. And then once we have that, we can use the point slope form because f of a is negative 6. So using our definition that we've already written down a few times, f prime of 3 is just the limit as h approaches 0, again, of f of 3 plus h minus f of 3. Again, I'm not using a anymore, I'm just using 3 for this specific example. My function is the parabola. Even though I don't have f of x, y is meaning the same thing as f of x. Y is a function of x. So I can use that parabola. I can plug in 3 plus h anywhere I see an x. So 3 plus h squared instead of x squared minus 8 times 3 plus h instead of 8 times x plus 9 minus f of 3, which is 3 squared minus 8 times 3 plus 9. So now, just like we've seen many times before, multiply everything out, simplify, then we're going to factor out an h, we'll simplify again, and then we get to use direct substitution. So multiplying out in the numerator, 3 plus h quantity squared is 9 plus 6h plus h squared minus 8 times 3 plus h, so that'll be negative 24, and then minus 8h plus 9 minus, I've got a 3 squared, which is 9, a minus of a minus 8 times 3, so that'll be a plus 24, and then a minus of 9. You can see that we've got a bunch of stuff that we can cancel out already. That 9 and this 9, that 9 and this 9, and then that 24 and that 24. And we still have all of this stuff divided by h. You can see that I've got a 6h that I will be able to combine with a negative 8h. So that gives me a minus 2h, and I still have that plus h squared. I've accounted for every term in my numerator this time. So now I get to factor out the h, which leaves me with a minus 2 plus h. I can then cancel out the h. Hopefully you're starting to see the pattern here of just evaluating, simplifying, getting to a point where you can factor out h, and then on the home stretch, you get to use direct substitution. So when h is equal to 0, I get negative 2. And remember what this is, that's the slope. So we can say that f prime of 3 is equal to negative 2. That's my slope. So then the equation, remember using what I wrote down before, y minus f of a equal f prime of a times x minus a. In this case, f of a we said was negative 6. That comes from the point 3 comma negative 6. F prime of a is our slope we just found, negative 2. And then x minus a, again, we said was 3. So I can simplify this. Y plus 6 equal to negative 2 times x minus 3 if I want to leave it in point slope form. Or if I distribute the negative 2 and then get the y all by itself, I get that my equation is just simply y equal negative 2x. So another example of finding the equation of a line that's tangent to a curve at a particular point. And so now this whole idea doesn't just apply to tangent lines and to velocities. We can now generalize this even further. On our way to this derivative, we did look at average velocities and also average rates of change. If we think of the average rate of change of any function, f, over an interval x1 to x2, then what we get as a concept is that the change in output divided by the change in input, that is our average rate of change, we can write that as delta y divided by delta x. That's what this little symbol here is, delta. And that's just, again, y2 minus y1 divided by x2 minus x1. Or in the case of using a function, f of x2 minus f of x1 divided by x2 minus x1. Then the instantaneous rate of change, just of the function, not instantaneous velocity, but just general instantaneous rate of change, is found by making the interval smaller and smaller, meaning x1 to x2 make that very small, which means that delta x approaches 0. Thus, we get the following. Instantaneous rate of change, as in general, is equal to the limit as delta x approaches 0 of delta y divided by delta x. You could also write this using the difference quotient as the limit as x2 approaches x1 of f of x2 minus f of x1 divided by x2 minus x1. The derivative f prime of a is the instantaneous rate of change of y equal f of x with respect to x, meaning the independent variable, when a is equal to a. So let's see a different concept then, using this idea of instantaneous rate of change, something outside the idea of tangent lines and velocity. This comes from number 51 on page 151, and I'm just going to look at part B of this question. The cost in dollars of producing X units of a certain commodity is capital C of X, which is equal to 5,000 plus 10x plus 0.05 x squared. So in this case, capital C is measured in dollars, and then x is just the number of items of a certain commodity. And we're just going to take a look at part B. Find the instantaneous rate of change of C with respect to x when x is equal to 100. Really what we are asked to find is this, C prime of 100. That's just using the language of what we saw up in this definition. Now this is going to be called marginal cost. We will see a little bit more about that in chapter 3. But I do want to actually find the meaning of the value once we actually calculate it. So let's calculate it first, and then we'll talk about the meaning. So C prime of 100, just again using our language, is the limit as h approaches 0 of C of, in this case, 100 plus h minus C of 100 divided by h. So again, calculating this is no different than what we did in all the other examples in this section. So we know that we'll just use our function to plug everything in. So everywhere I see an x, I'm going to first replace it with 100 plus h. So my function starts off with 5,000, then 10 times x, but now it's going to be 10 times 100 plus h, plus 0.05 times x squared, but now it's 100 plus h squared. And then minus my function now evaluated at 100. So 5,000 plus 10 times 100 plus 0.05 times 100 squared. And then this is all divided by h. So just expanding my numerator, 5,000 plus 10 times 100 plus h, so that's 1,000 plus 10h plus 0.05 times, when I square the binomial, I'll get 100 times 100, which is 10,000, plus 2 times 100 times h, which is 200h, plus h squared. And then I have minus 5,000 minus 10 times 100, or 1,000, and then minus 0.05 times 100 squared. So 0.05 times 100 squared is 500, and I'll be subtracting that. And this will all be divided by h. Let's go ahead and cross a couple things out just to save some space here. The 5,000s will cancel out, as will the 1,000s. Now let's just distribute that 0.05. So first, 0.05 times 10,000 will leave us 500. 0.05 times 200h will give us 10h. And then plus 0.05 times h squared. And then I still have minus 500. So we get a little bit more that cancels out. Okay. I forgot another piece, didn't I? This 10h right there. So he's going to go right here. So this means that I have the limit as h approaches 0 of, I might as well add those two 10h's, so 20h plus 0.05 h squared, all divided by h. I'll factor out my h. I can then cancel out my h's by division. And then finally, I can evaluate. And I get 20 plus 0.05 times 0, because I'm evaluating h equal to 0 with the direct substitution property, and I get 20. So now here's the one thing that we do want to remember from the velocity question. We had units of measurement for instantaneous velocity, and it was meters per second. So our units here should be something per something. And what we want to think of this is it's the output units. Just like in our velocity case, the output was meters per input units, which in our velocity problem, it was time. In this case, our input units is just simply the number of items. So units of our commodity. Our output unit of measurement is dollars. And so our answer here is $20 per unit. So now let's discuss the meaning of this. What is the meaning of $20 per unit? What this is saying is that if we increase production by just 1 unit, meaning X increases by 1, the number 1, then our cost increases by $20. So when X is equal to 100, when the amount of production is 100 units, if we increase the number of units as in X by 1, then the cost goes up by $20. And we see that just from the units of measurement for our answer. So again, this is called marginal cost, and it is an important concept from calculus. There's actually a whole class called business calculus, and they focus a lot on this. And it's a good one to point out because it's good to notice that this idea of the derivative applies to many more things than just tangent lines and velocities. And we will see more of those when we get into later sections.